In Chapter 8, we're going to focus mostly on how to graph quadratic functions. And quadratics are the simplest polynomial that you can have that is nonlinear. Um, we achieve this nonlinearity by putting an exponent on the variable, on the x, and that exponent causes the graph to no longer be a straight line. Quadratic functions are going to have this general format, uh, ax squared plus bx plus c. And hopefully this looks familiar to you from chapter 7 when we learned how to multiply polynomials and how to factor polynomials. The type of function that we're talking about when we have this x squared term in our polynomial is called a quadratic, but the shape that the graph creates is called a parabola. Uh, and those two words are connected to each other. They're sometimes used interchangeably, even though they look so different. It's not like a linear equation that makes a line where the two words appear to be very similar. A quadratic function creates a parabola shape graph. The simplest quadratic function is x squared. And then we will find out over the next few lessons how we can transform this most basic quadratic function into more into a wide variety of U-shaped graphs. There are two important vocabulary words we need when discussing parabolas, and the first of those words is vertex. So vertex is going to be the inflection point on a parabola, the lowest point on a parabola that opens upward, or the highest point on a parabola that opens downward. And I will refer to happy quadratics, happy parabolas, and sad parabolas, depending on which way the U shape opens, whether it opens up for a happy parabola or opens down for a sad parabola. The other thing we need to recognize is that parabolas are symmetric. There's a vertical line that is a line of symmetry uh, for the parabola, and being able to identify that line of symmetry is important. The line of symmetry always goes through that vertex point, and so the vertex and that axis of symmetry are closely linked together. So let's look at an example here. Y equals x squared plus 2x minus 3, and look at how we uh, identify some of the key characteristics of a quadratic function or a parabola. First of all, the vertex. We want to list the coordinates, the x comma y coordinates of the lowest or highest point on the parabola. For an open upward facing parabola, we want to choose the lowest point, and our coordinates here are -1 comma -4. The axis of symmetry is the kind of the imaginary line that passes vertically through the vertex of a parabola. And so the equation for a vertical line is not written as y equals, written as x equals. So x equals -1 in this case. Domain and range. Domain is all possible x values of for a particular graph. And in this graph, there is no restriction to my x values. I can continue uh, kind of to the negative x's as far as I like. I can continue to the positive x's as far as I'd like. So the domain for this function is all real numbers. And in fact, this is true for all parabolas. All parabolas have a domain of all real numbers. The range of a parabola is a little more complicated. The range, if you look at these y values, for this particular parabola, because it opens upwards, I can continue in the upwards, the positive infinity direction of y forever. But in the downward direction, I'm limited by where the vertex point is. So in terms of my possible y values, y must be greater than or equal to -4. Notice the connection to what we saw for the vertex. That -4 number is the y value of the vertex point. Um, what's increasing, what's decreasing on this graph? So if we highlight kind of increasing in red, what we do is this is as we read the graph from left to right, does the y value go up for increasing or go down for decreasing? And as I read the graph from left to right, kind of starting at the vertex point and moving up is where I see that the graph is increasing. Whereas, where's the graph decreasing? Uh, that's anywhere kind of before the vertex point. So for increasing, we want to list the x values where those y values are getting higher and higher. And so the x values for the region that I've highlighted in red are where x is greater than 0. And for my decreasing values, that would be the x values that are less than 0. It's important to realize that neither of these inequalities includes the term 0 or includes the value 0 because when x equals 0, the function is neither increasing nor decreasing. It's totally level, totally flat. The slope is 0. Um, Next, y-intercepts and x-intercepts. Um, the y-intercept, there's only one for any given parabola, and oops, uh, this one is the y-intercept occurs at -3, so the y-intercept is here at -3. And the x-intercepts, there are two of them for this particular parabola. I have a y-intercept over here at -3 and another one at, I'm sorry, x equals -3 and at x equals 1. Next feature to look for, where's the graph positive and where's the graph negative? Positive refers to where the y values are positive or negative. So where's the graph above the x-axis and where's the graph fall below the x-axis? But once again, we want to list x values. Even though we're talking about y values, we want to list the x values where this is true. So where is this graph positive? It's positive above the x-axis here. And you can see that there are two locations where this graph is positive. So this is when x is less than -3 and where x is greater than 1. Notice the relationship between these values and the x-intercepts. The x-intercepts tend to be the cutoff points above which or below which you change whether the function is positive or negative. If we now look at where the graph is negative, the graph is negative when we're below the x-axis. And so on this graph, that occurs for the x values that are between -3 and +1. And again, observe that relationship with the x-intercept values. It is between those x-intercepts where we change whether the function is positive or negative. Let's look at end behavior. There are always two sentences to discuss for end behavior. The first one is, as x approaches negative infinity, what happens to y? And so as we go move in the x direction, kind of out towards the left, towards negative infinity, what's happening to y as we move further and further and further in this direction? And I can see from the graph here that I'm going to continue upwards and upwards in the y direction. So as x approaches negative infinity, y approaches positive infinity. Of course, there's also a positive end to this. what happens as x approaches positive infinity, as we keep on moving further and further and further to the right. Um, Once again, I can see an arrow here indicating that the y values get bigger and bigger and bigger. So again, y approaches positive infinity for this particular parabola as we move to the right on the graph. Of course, the values will be different for different parabolas, and if your parabola opens upwards, opens downwards, then for end behavior, for example, the y will approach negative infinity in both the negative x direction and the positive x direction. So let's look at kind of making some changes to the basic function to see how we end up with kind of a parabola that looks like the example that we just did in question A. So if we graph a function like g of x here, where it's 2 times x squared, how does that compare to the original parent function, x squared? Well, here in as f of x, I've got this original uh, x squared function drawn here, and I've got it graphed here in red. And so now we want to kind of compare this to the new g of x function. And notice that I'm taking my f of x function and just multiplying it by 2. So any output values I had before, I'm now just multiplying these by 2. So instead of having an output of 4, I have an output of 8. Instead of having an output of 1, I have an output of 2. Instead of an output of 0, well, I still have an output of 0. Output of 1 becomes an output of 2. Output of 4, double that is 8. On here, my vertex stays the same. But when I move kind of 1.1 unit on either side of that vertex, I go up to 2 units instead of just 1. And then when I go move 2 units from the vertex in the x direction, I plot points that look like this. So I end up with a narrower version of the parabola when I have a multiplication value, an a value in front of my x term. So what didn't change about the graph? Well, both graphs open upwards. Um, both graphs share the same vertex and therefore the same vertical axis of symmetry. But in terms of what's different, we can see that G is narrower than F. And the reason for this is because we've actually done a vertical stretch. So G is a vertical stretch of F by a factor of 2 because of that 2 multiplication value. So G is being stretched, and that stretching causes the resulting parabola to have a narrower shape. So let's look at what happens if we have a different multiplication factor. This time we have a negative a value, and also our a value is a fraction. So let's see what happens when we graph this. We can choose to graph whatever x values we want to choose if we want to plot a graph. But I am going to choose x values that are multiples of 3 because my function has a 3 in the denominator of the fraction, and it'll just give me nicer output values if I input a value that's a multiple of 3. So I'll test 0 in the middle, but then I'll test -3 and -6, as well as +3 and +6. So if once again, when I input the number 0 into this function, I get an output of 0. But if I input -3 and I square that, that's 9. But then if I take -1/3 of 9, that gives me -3. And -6 squared is +36. And if I take -1/3 of positive 36, that gives me -12. And then on the right side of the equation, I end up with, or right side of the data table, I end up with kind of symmetric points on the positive side of 0. And when I plot these points on my graph, I end up with a downward facing parabola that looks like this. Notice my vertex is the same, my axis of symmetry is the same, but this time my parabola opens downward. This is a reflection, so H is a reflection of F because of the negative sign, because A is negative. And another thing that happened is notice that this parabola looks wider than the original parabola. That's because of this 1/3 is a fraction that's less than 1. So we've had a vertical shrink or compression. This vertical shrink, it's almost like sitting on the parabola, kind of makes it spread out wider. So H is vertical shrink. And that is because 1/3 is less than 1. And that's what makes H wider than F. So if we look at a real world example of parabolas, satellite dishes really are parabolic in shape. This helps kind of focus signals uh, to their kind of receptor point here on the satellite dish. So this question is asking us to determine the dimensions of the satellite dish. What's the width? What's the depth of this satellite dish? And we're told kind of the points here on the parabola, and we can see uh, that the domain kind of ranges between -2 and x and +2. And we can see that the range ranges between 0 and +1. So if we take those extreme values and subtract them from each other, imagine if you're on a football field, if you're at the 40-yard line and I'm at the 30-yard line, how far apart are we? Well, we're 10 meters apart or yards apart because we are, you subtract those values to determine the distance between the point where you are and the point where I am. And so we do the same thing here. We do 2 minus -2, which equals 4. So the width is 4 meters. And then we similarly do a subtraction of the extreme values on the range. 1 minus 0 is 1 meter as our depth. So those are the dimensions of this satellite dish. I hope this helps.